Okay, so video 4, we're turning now to Isaac Newton's view in response to Descartes, as I've said. So, as I've already said, already explained as best as I can, although it's difficult, as I've said, without getting feedback from people. Descartes' view then was, you think of it as I'm calling it, this friction notion of true motion. What is real movement? Well, it's when something basically rubs up against another thing, or when that thing moves relative to its immediately surrounding contiguous contiguous matter. That was his definition, and he thought that gave rise to that's what gave rise to force, right? The idea of a force. So it was based upon empirical observations that Descartes had made. He'd noticed that friction causes heat if you rub your hands together and so on. So he's got this idea that's what true motion is, when one thing kind of rubs up against another. Okay, so Newton, as I've said, his most famous book is a picture of the first edition, the Principia Mathematica, and it's the most important book in the history of science, I should think, and I think even more important than Einstein's view. So Einstein often gets thought of as being some, kind of a genius, and he was certainly a clever bloke. I'm not going to deny that, but he wasn't of the same stature as Newton. Newton kind of single-handedly invented modern physics. Einstein was working within a tradition, and a well-established tradition at the time, and really just took some of the results further forward. Newton this guy was, by the way, a very strange guy was Newton. A couple of things that you might be interested to know, I suppose. Why not pepper these lectures with a couple of mildly interesting facts, I suppose. So the first one is, how many colours are in the rainbow? And if you answer 7, I know that's the standard answer, but it's actually not 7. There are only 6 colours in the rainbow. So I know red, orange, yellow, green, red, orange, yellow, green, blue, indigo, violet. Is that the usual ones that people say? Anyway, the point is, that is 7. Indigo and violet are not two separate colours. So Newton did a lot of work on light, and it was a division which he put in arbitrarily, because he thought that 7 was a lucky number. So, we think there are 7 colours in the rainbow because Newton was superstitious, basically. So it's a strange guy. He spent years of his life working on alchemy, trying to turn base metal into gold, for example. And also did all sorts of experiments on himself. There were times apparently he used to walk around with his eyes bandaged up because he used to stick pencils and try to prise around the back of his eyes to see what effect it had on his vision and all sorts of stuff. Anyway, an interesting chap and clever. So, in the Scholium, so this is the kind of the introduction to the Principia Mathematica, where he kind of justifies his whole overall approach that he's taking. He gives this kind of a basic argument. So this isn't contained in it as premise conclusion form like this. This is drawn out from the Scholium. He basically he wants to argue against Descartes' view. He needs, so as we've said, it turns out that you need this notion of true motion. In order to get the physics or the science to work, you need some things to be moving, undergoing true motion. And it's true motion, as I've already indicated, which is supposed to give rise to forces. Okay? And Descartes thought that true motion was friction, if you like, and that's what the force was, one thing moving relative to its immediately surrounding matter. So, okay. Newton knows he needs true motion, and he's going to attack Descartes' account of what true motion is. So he says, look, material bodies undergo true motion. That he knows he needs. If material bodies undergo true motion, then they must move relative to absolute space that exists independently of any material body. Alright, so that's the substantivalist view, in direct opposition to Descartes' relationism. Therefore, absolute space exists independently of any material body. I mean, it's just a simple, it's a simple modus ponens argument, right? There we go. Okay, so that's the basic argument. What he needs to establish then is premise 2. So premise 1 we're taking for granted. Descartes agreed with premise 1. I mean, we do need the idea that material bodies undergo this true motion, which is supposed to give rise to the idea of a force. So then the question is, well, okay, well, yeah, how do we get premise 2? And it's Newton's bucket experiment. And he outlines this, and this is an empirical experiment. He'd actually done this, and the whole point of this experiment is to show that Descartes' view is wrong. Okay, so this is, I mean, I'll try maybe to illustrate this. I'll maybe go to my drawing pad in a minute. But the idea here is that we start off with a bucket of water, a bucket filled with water, hanging on a string. Okay, and then we twist the bucket up, so we carefully just twist it round so that we've got the string is all sort of in a it's then in a well, twisted, so when we let it go it means that it's going to start untwisting. Okay, but if we do that, so we twist up the string with the bucket, and then at point B, so we're holding it still, the water is still inside the bucket at this point, then we let it go and we see what happens. And it turns out that what happens is the bucket starts to move, and the water to begin with stays flat inside the bucket. So the water doesn't move, but the bucket does, right? But then, as the bucket spins, the water begins to sort of turn with the bucket until eventually the water inside the bucket is turning along with the bucket itself. Okay? Hopefully that makes sense. So that's the second point. The bucket starts to twist round once you let it go, and the string begins to untwist. And the bucket rotates, but the water doesn't. But as you leave it, the water slowly starts to move, and it starts to spin around with the bucket until at point C here, yeah, the water and the bucket are both in rotation together. That's the idea. And here is what we should observe about this. The thing that we need to observe is that at the start of the experiment, as the bucket is beginning to move round, starting to spin round, and the water is not moving, the surface of the water is entirely flat. But then, at the point at which the water catches up with the rotation of the bucket and is spinning along with it, we then get this dip in the water here. We get this, what do they call it? Do they call it a meniscus? I've forgotten what it gets called. Yes, I think it's called a meniscus. I just looked it up, and it is called a meniscus. I had to stop the recording and looked it up. Yeah, so a meniscus. It's also the name of some part of the body. That's what threw me. Anyway, so hopefully that makes sense. So we've got this experimental setup, and if you can do this experiment yourself, try it at home, and you'll get this result if you set it up carefully. So okay, what's the significance of this then? Why is this interesting for Newton, and how does it bear upon Descartes' view? Okay, so here's how. Remember that Descartes defined true motion in terms of movement relative to immediately surrounding matter. That is the kind of, as I keep putting it, this friction view of true movement. And that's what's supposed to give rise to the operation of forces, according to Descartes. Well, okay, consider what happens at the point when you just let go of the bucket here and it starts to spin around. Well, there, the water is moving relative to the bucket, right? As the bucket is spinning around the water is, as it were, rubbing. There's going to be, I mean, you don't normally think about water as creating friction, but there will be. There's the bucket and the water are kind of going to be rubbing up against one another as the bucket is spinning round, okay? So at that point, Descartes will have to say, at point B, when the bucket starts to spin and the water doesn't move, at that point, the water is undergoing true motion, right? But then later on, as the water catches up with the bucket and spins round with the bucket at the same time, Descartes will at that point say, because at that point the water isn't moving relative to the bucket, so it's not rubbing up against the bucket, it's moving with it. At that point it's at what we might call true rest. Okay? So in other words, at point B, when you first let the bucket go, the water is at its maximum true motion according to Descartes. By the time we get to point C, it's then at true rest. So it starts off in maximum true motion and decreases until you get to point C, when the water is then at true rest, in Descartes' definition of true motion and true rest, that is. And Newton's thought here is simply this. Hang on, true motion is what is supposed to give rise to the operation of forces. And the operation of forces is supposed to give rise to the observation of physical effects. But at point B, when the water is undergoing maximum true motion, the water's flat. You get no physical effect whatsoever. It's only when you get to point C, when supposedly the water is meant to be at true rest, that we see the operation of the forces. We get this meniscus. So therefore, the physical effects are anti-correlated with true motion here, and therefore Descartes must be wrong about the notion of true motion. Right. So, I wonder whether that's made sense to you. Again, it's difficult without having feedback. But okay, we talk through all of this in the seminar, and I should say, maybe worth saying this by the way, if this kind of stuff doesn't grab you, this is almost like a history, to do with the history of science, and it's the crossover between philosophy and science, and if this doesn't grab you, we won't really be doing too much more of this in later weeks. So in later weeks we'll be sticking with, pretty much pure philosophy. Apart from the last week where we will return to some physics. Alright, so there is Descartes, Newton's argument at any rate against Descartes' view. So what are his conclusions here? Well, he says, look, true motion shouldn't be defined as Descartes defines it. How then do we define what true motion is? And he says, and this is a bit of a tricky notion again now, he says, well, true motion happens in terms of change of velocity relative to absolute space. So I wonder, you see, I'm never quite sure how much knowledge people have got of these notions. So velocity is speed with a direction. So you can think about it as, in other words, if you're moving in a straight line at a certain speed, you're moving at a straight line at a certain, velocity, I want to say. Movement in a straight line is movement with a unchanging velocity. Well, that's a terrible explanation. I'll keep wanting to say speed. Anyway, velocity is travelling at a certain speed in a single direction. And what that means is if you turn a corner, right? If you not only is accelerating and decelerating changes of velocity, the point is so is kind of moving left and moving right, or rotation, in fact. So that's the important point. Rotation turns out to be velocity. So as the water in the bucket, in the example just given, spins, its turning, its spinning is a change of velocity. Okay. I don't think I explained that very well. Maybe I'll have another go at that. Let me have another go at that just to see if I can get this right. So, velocity is, you can think about that as just being like a speed. So 30 miles an hour is a velocity, and you can change velocity in three ways. The first way to change velocity is by accelerating. So if you speed up, you go from 30 miles an hour to 40 miles an hour, travelling in a straight line. That's acceleration, so that's a change in velocity. Another way to change velocity is to decelerate. So put your foot on the brake and go from 20 miles an hour to 30 miles an hour down to 20 miles an hour. That's a change in velocity as you slow down. And a third way to change velocity is to swerve to the left or the right. Okay, so a change in direction is also a change in velocity. Okay, that's a bit better, I think. I think I've explained that a bit better there. So if we then go back to the bucket experiment, the point here is the water at the beginning on Newton's definition of true motion, which is this change of velocity. At this point, it's not moving at all, or rather, it's not undergoing any change in velocity. But by the end of the experiment, it's undergoing a change in the velocity because it's rotating, and rotation is a change in velocity. So the reason why we see the physical effects here is because true motion for Newton is change in velocity. I hope that makes sense. But the point is, if you're going to have change in velocity, Newton says, well, you've got to have change in velocity relative to something, right? And it got to be relative to the existence of an absolute space, a background absolute space. So yeah, you can think. So I drew that grid earlier in the previous video and trying to explain Descartes' view of a kind of a background grid into which things are put, and that's what Newton's view is like. And the thought here is, when things speed up or slow down or change direction, that gives rise to forces, but it's speeding up and slowing down and changing direction relative to this background grid, right? So you take the background grid as the fixed point, and when things speed up within the grid, and when things slow down, and when things swerve, that's when we see empirical effects. And the whole of Newton's scientific view is premised on this, and it's premised on a view that he got by responding to Descartes. Now the one thing here is, there is an interesting aspect to all of this, and it's that absolute space, so we'll talk about time in a minute. I mean, it follows the same line. It's easier to talk about in terms of space first of all. But absolute space is a theoretical posit of Newton's theory. That is, it's not observable. You can't see absolute space on Newton's view. There's no sense in which you can measure its existence, or it doesn't look like there is, right? And that's because, well, it's just not observable. You can only observe material objects. What you can do is or Newton thinks you must suppose it's there in order to see that we get these kind of forces that occur when things move relative to it, or accelerate, decelerate, or change in velocity relative to it. But it's not something that you can actually see. So it can't be observed in any sense on Newton's view. Okay. Now, let's turn to what he says about time then. Now, he's very clearly then a substantivalist about space. Right? That's the spatial stuff, that background absolute space must exist. But he never actually and he kind of says this, he actually explicitly says that the space exists independently of the material objects and so on. But that commits him, he doesn't commit himself, he doesn't explicitly say that about time. He only says about time that it flows equably, is his phrase. He talks about a kind of objective flow to time. But notice that Descartes also held that the flow of time was objective, so the existence of time was objective. Right? Because Descartes thought that the idea of material objects having duratio, having this sort of and the way to think about this is, time can flow even if nothing changes. So on Descartes' view, that's true. You could have a completely static universe. You'd have no tempus, you'd have no measurable change, but you'd still have time going on, you'd still have duratio. And Descartes, so can Descartes and Newton agree about time in this sense? And might you think, well, is Newton's substantivalism compatible with the relationism about time? So can you be a substantivalist about space but not about time? And the answer here is no. And in Newton's view, absolute space exists independently of material bodies, right? But more than that, it persists through time. So, on Newton's view, you really could have a completely empty universe, empty, no material objects whatsoever. All you've got is absolute space, this kind of grid into which you might put objects, and that grid can persist through time. So it's a really kind of a bleak universe of just a kind of empty space with time flowing. So on Newton's view, you can have that, and it drops out from... I mean, it's this, right, really? It's like the only way that Newton thinks you can explain the physical forces that we see is by admitting this. So there's this empirical element to all of this, and he thinks that Descartes' account has just got things wrong. It's worth noting that the bucket experiment is one illustration of it. Newton had many more illustrations of where Descartes' account gets it wrong. So he doesn't rest it all upon, doesn't rest his case upon only the bucket experiment, but that was one that he used to sort of dramatise or to illustrate the fact that Descartes' view was wrong. Okay, so that's Newton. Now we're going to move to, the next thing we're going to do is we're going to move to Leibniz, Gottfried Wilhelm Leibniz.